All right, it is March 31st, Tuesday, and we are talking about the Claisian condensation, and we are doing Model 1, your last Poggle 23C, and it's page 280. All right, so the Claisian has, starting material is the ester, and we're going to use sodium methoxide because we want to match the methyl ester here. So this is methyl for the methyl, and then it's acetate. This is the starting material, and these two come together to make a beta keto ester. That is your Claisian condensation product. There's your beta keto, and then I'm going to draw the ester. Okay, so question number one. How many carbons in the carbon framework of the methyl acetate, not counting the OCH3 group, are there? So in the methyl acetate, 1, 2. So hopefully you answered 2. B, how many carbons are in the Claisian product, not counting the OCH3? So you have 1, 2, 3, 4. 4. How many molecules of methyl acetate combine to form the Claisian product? See the number 2? So the answer is 2. Circle each acetate portion in the Claisian product. Okay, so the acetate portion is this portion right here. That's acetate, 2 carbons. So it's here and it's here. So that's the acetate portion. Okay. E, using Greek letters indicate the position where the new carbon-carbon bond. So you look for your carbonyl of your ester, and then that's your alpha and that's your beta. So this is your new alpha beta bond. Compare the starting material to the product. What group has been eliminated? So you're going to have a leaving group here, okay? Esters are a good leaving group. Remember, we did this the first week of organic 1, organic 2. And so that's going to be your leaving group. Okay, so the OCH3 is a good leaving group. So when we form our tetrahedral intermediate, like we did with the aldol, instead of we're not going to protonate. We're not going to protonate the beta hydroxy. Okay, we're not going to protonate that. Instead, we're going to reform a carbonyl, and OCH3 is your leaving group. Okay, and that's how this mechanism differs. Yes, you need to know this mechanism, so you should have that on your sheet. Recall the aldol condensation. So on here, they're telling you to recall the aldol condensation. This is problem number 2. So this is your aldol condensation. You had an enolate here, which is your nucleophile, and this is your electrophile. Okay, and so what happens is this nucleophile attacks the electrophile. This is your alpha, this is your beta, and then those electrons go up. And so that's your beta, this is your alpha. Okay, and then this gets protonated. So this is what we're talking about. This gets protonated. How is the nucleophile generated? You use base. Remember, you use sodium hydroxide. It deprotonates the alpha carbon. Okay, so 2b. Compare the aldol condensation to the Claisian condensation. How is the Claisian similar to the alcohol? Step 1 is the same. Okay, you're going to deprotonate your alpha carbon hydrogen to make your enolate. Okay, and then step 2, the enolate will attack the carbonyl of your other molecule to form an alpha-beta bond, the tetrahedral intermediate. So you're going to get the tetrahedral intermediate. Okay, that's going to be the same. So that's how they're similar. Okay, now we're on problem 2C. Draw the enolate ion that is formed from reacting the methyl acetate with sodium methoxide. The enolate will react as the nucleophile. Okay, so the enolate is always the nucleophile. So you got to find your alpha carbon. There's your alpha carbon. Draw in your hydrogens. So I want to see this labeled. Okay, now this is your base. It's going to come and take that hydrogen and form your enolate. Okay, so there's your alpha carbon. Devise a mechanism for the Claisian product using curved arrows to show electron movement. Okay, number 3 is important, all right? Because you need to get this in your notes because you're going to have an open response question on this on your quizam. Remember, you get 5 open response questions. So the mechanism of the Claisian will be one of them. All right, so this is your reaction. You would see something like this. All right, and you have to do the product and you have to draw the mechanism. So you have to draw one of these. The first step is to make your enolate. Okay, so you locate your alpha carbon, you draw in your hydrogens, and then these electron, we'll take those. You see how I do my 2 electron flow arrows? All right, so now you show your enolate. And now it's going to attack another one. So we draw another one. So draw another one here. Okay. And this is going to be your, see I do a delta positive, not a full positive. This is your beta. This becomes your beta carbon. Okay, your electrophile. This is your nucleophile. This is always your alpha carbon. So now we have the electron flow arrows. The nucleophile attacks the electrophile to form a tetrahedral intermediate. That's the same. I'm going to draw that. I'm going to draw first my alpha. Okay, so this is my alpha. You just draw it just the same. You can make that red carbon, if you will. And then it's going to attack my beta. So there's my new bond, my beta. And this is going to form a tetrahedral intermediate. Now I got to make sure I get everything off of this. So I have this here, tetrahedral, 4 things. And then I have OCH3. See my OCH3? Okay, now this is what's different. Okay, we're not protonating this anion. We reform the carbonyl. OCH3 is your leaving group. So electrons go here towards the beta, these leave. Okay, so you're going to lose OCH3, right? That's your base. So all you're doing is regenerating that, and then you have your carbonyl, which is your beta, and then you have your alpha, And then you have your rest of your compound. And that's your mechanism. Beta, keto, ester. And that's the product of the Claisian. Number 4. Like the aldol condensation, the Claisian can also afford mixed Claisian products. Consider the reaction of an ester. So, by the way, this pKa is 24 for the alpha carbon. This pKa of this alpha carbon is 20. Okay, we're talking 10,000 times more acidic. So if you have both of these in base, like sodium ethoxide, which you'd have to, so you don't saponify that, which one is going to be your enolate? That's right, it will be the aldehyde. Okay, that'll be your enolate. And that's what we're talking about here. So, which compound is more acidic? Ketone. Which compound is most likely to act as the nucleophile? Of course, this is aldehyde, but it is a ketone or an aldehyde. Okay, because it's 10, and I put explain, because it's 10,000 times more acidic. So it's going to get deprotonated first. And once it attacks, it's an irreversible reaction. Okay, so now we're going to page 282. We're dealing with B. Draw the enolate form from the ester and the ketone shown below. Explain why the ketone has a lower pKa than the ester. All right, well, we got to draw resonance, right? Draw the conjugate acid. So they're saying pKa 20 here, pKa 24. So just go ahead and make your enolate. Okay. Resonance structure. So you have electron donating group here. Here. Okay. Just be quiet. Sorry about that, folks. The child is using the blender. It might get a little loud in here. All right. All right. So this is comparatively, if a CH3 versus an OCH3, this is more of an electron donating group. Okay, and this would be the inductive effect because they have the same number. Okay, so that's the reason why it's 10,000. Okay, so it says draw the mixed Claisian product that results from the base catalyzed reaction. Okay, so let's go ahead and draw this reaction. You're going to have to do these reactions, okay? So, and you're going to have to look at both of them and figure out which one's going to be the enolate and which one's going to be the beta carbon. So you would get something like this. And you would want to do that in sodium methoxide, like I said, so you don't get transesterification or saponification. And now we have to draw the product and the mechanism. So here you got to say, okay, here's my carbonyl. I could have this as an alpha carbon, or this could be an alpha carbon, right? And then you're like, well, okay, there's two alpha carbons. This is the pKa is 20. This is a pKa of 24. So the ketone or an aldehyde will be the enolate over the ester. Okay, so then you can do your base here and draw in your alpha hydrogens because you're going to do your mechanism here. And you show your enolate. So I like for you to label alpha and draw your alpha hydrogens and show this step with electron flow arrows. Now this is your enolate, and your enolate is going to attack the, so this is your nucleophile, and this is your electrophile. Okay, so here we have these electrons going here. This is going to be your new beta. And when we redraw this, I always draw, I come over to the right hand side and I draw my enolate the same way, and then I say, okay, this is my alpha carbon here, and then I go here and say, okay, there's my beta, so there's my beta, and when I form my tetrahedral intermediate, okay, because those electrons come up, and I gotta have 4 things on this. So here we have this carbon here, and then we have an OCH3. Now what's different, right? This is going to reform, make this green, reform the carbonyl, and this is going to be a leaving group. And so and I didn't draw that right, sorry folks. So this is my alpha, there's my alpha, I just check my redrawing, and this is my beta. And that is the mechanism. Okay, so that gets you to Model 2. We can do Model 2 today. Okay. Model 2 is another reaction, and so right now you should have an aldol reaction sheet. You should have Claisian. You also have alpha substitution. You did that with LDA and then an alkyl bromide. Okay, and the 4th reaction is here, the acetoacetic ester synthesis. I bet you have about 10 reactions in this chapter, okay? So, because we're going to have probably 5 or 6 reactions that are, you don't have POGL, because this is your last POGL. So, all right, Model 2. This is called the acetoacetic ester synthesis. And you start with the starting material, which is called acetoacetic ester. Okay, so this is aceto, is this. This is aceto. And acidic, because there's 2, is an ester. So this is the acidic ester. And the acidic group is what's your key component of vinegar, acetic acid. Okay, once again, what base are we using? These are all using bases for our reagents. The sodium ethoxide, because this is our base. We don't want transesterification. And then the second thing you're going to do here, the second step will be the RX, okay? So this is going to be your primary alkyl halide. So you've seen this. We're combining what you saw here in the Claisian, and also number 3 with the alpha substitution. Okay, so the first thing, oh, well, let's just continue on. And your product then, if you see that this is your alpha carbon, so you get this, your alpha carbon then gets whatever R is there, okay? So which 2 functional groups, let's do 1, or 5A, which 2 functional groups are in acetoacetic ester? Okay, a ketone and an ester. And that's the toe, acetoester. Label the carbons of the acetoacetic ester with Greek letters with respect to the ester group. Okay, so we already did the alpha there, and there's your beta. Okay. With respect to the ester, what position is the ketone group on? It's on your beta carbon. Could acetoacetic ester be prepared from a Claisian condensation? Well, let's figure it out. This is your alpha, beta, and we draw the line. Okay? So then we draw the synthons, right? So there's your beta, and here's your alpha. All right. So then what? So there's your aldehyde. Or no, that wouldn't work. Sorry, because you have a keto there. Keto. So because this is a keto on the beta, this has to be OCH3. Or well, in this case, it'd be ethyl. Because you want to keep the esters the same. So this would be O. So this actually is a self. And you can do the chemistry then. O ethyl. Okay. This becomes your enolate. And then this would attack here. And you would get this intermediate. So that's your beta. This is your alpha. And then those electrons come. This is your leaving group. And you form this is your aceto acidic ester. So the answer is yes. How many acidic alpha positions are present in the acetoacidic ester? So you have this one here and this one here. So the answer is 2. Draw the enolate that would be formed by the removal of an indicated hydrogen in the structure shown below. All right. So we're on page 283. And this one's circled and wants to show that. Okay. So your base here would deprotonate and you'd form your alpha enolate. See my monkey face? All right, and then we show our resonance structure here. This goes here, this goes there. Or could have gone the other way. And this is your other resonance structure. Okay, so you have 3 resonance structures. Now, so that's an alpha carbon. And then you have a carbon here, right? The pKa. What is the pKa of this? So I'm going to look at your page 1184, table 22.1. It's in your slides. And that is a beta keto ester. And the pKa there is 11. Now that's different than this one. Okay, the pKa here is 9 because the difference is the ester versus the ketone. All right, so then your next one where you could have taken off the other alpha hydrogen. Okay, so they're showing you B. What if you took this one and made your enolate? Okay, so you draw that. All right, and then you draw your resonance structure. All right, so you only have 2 resonance structures here. 1, 2. This one has 3. And that is why uh, this proton is more acidic on this alpha carbon, and it actually has a pK of 11. So which hydrogen of the two choices shown in 5C would be the most acidic? HA. And it's because of 3 resonance structures versus 2. Okay, in step 2, the enolate reacts with an alkyl halide. Okay, so in step 2, so once we generate this enolate, the first step is to generate your enolate. So let's draw that. So step 1, you have generated your enolate between these 2 carbonyl groups, and then you're going to react it with an alkyl halide. The enolate will act as your nucleophile. This is going to be an SN2. So the R group is your electrophile. And so you draw your mechanism arrows, your electron flow arrows. And there is the R group on your alpha carbon. The malonic ester synthesis. Now this is another one, folks. You need another sheet for this. This is reaction number 5, okay? Shown below. And you'll see why it's important. So this needs its own reaction sheet. So you need to add that in. That's number 6. So the malonic ester synthesis. This is actually called the malonic ester. It's actually a malonic acid is in the Krebs cycle. So if you're going on to take biochemistry, you'll be familiar with malonic acid. This is malonic ester. It has 1, 2, 3 carbons here. It is a structure you want to become familiar with. Okay, the base you'd want to use is sodium ethoxide because you have ethyl ester here. And then the second step will be to react it with a primary alkyl halide. Okay, and it's going to be the same step. Okay, it says note the similarities. Okay, so you just basically are going to have your ethyl ester there, and your R group is going to add at the alpha carbon. So what's the similarities? You have the alpha hydrogen is the nucleophile, your enolate, that's a similarity. Your electrophile is the alkyl halide, that's a similarity, and the alpha carbon gets alkylated. What about the difference? The difference in the malonic ester will be the end product, and it's because you have the difference is a diester. Okay, so you have a diester. Okay, and so here your product is a diester. There it's just a single ester. Okay. All right, now we're going into page 284. This is 30 minutes. All right. I tell you what, we're going to stop there and we'll finish on page 284 tomorrow.